Today we're going to talk about ideal gas and the law that goes along with it. So let's figure out what an ideal gas is compared to a real gas. So an ideal gas is one that follows the gas laws at all conditions of pressure and temperature. Its particles have no volume and no attractions to each other. As you can guess, this probably is not very realistic. So that's going to be the difference between an ideal gas and a real gas. A real gas does have a volume, and the particles do have some attractions with each other. The main difference between real gases and ideal gases is at its high pressures and low temperatures. At most other pressures and temperatures, our gases do behave like ideal gases, which is why we can follow the ideal gas law. So what is the ideal gas law? It allows us to calculate the number of moles that a contained gas requires. So we have to use the equation PV is equal to nRT. P is equal to our pressure, V is our volume, N is the number of moles that we have, R is the ideal gas constant, so it's just a constant, so its value is 8.31, and the units for it are liters times kilopascals over Kelvin times moles. And the temperature is T. So let's do a practice problem that uses our ideal gas law. So that's PV is equal to nRT. Alright, so here's an example. A deep underground cavern contains 2.24 times 10 to the 6 liters of methane gas at a pressure of 1.50 times 10 to the 3rd kilopascals. At a temperature of 315 Kelvin. How many kilograms of CH4 does the cavern contain? Alright, so the first thing that we should do here is write down all of our givens. So we know that our ideal gas law is PV is equal to nRT. Let's look at our givens here. It says that a deep underground cavern contains 2.24 times 10 to the 6 liters. So liters is our volume. So we have 2.24 times 10 to the 6 liters. What else does it give us? It says at a pressure of 1.50 times 10 to the 3rd kilopascals. Alright, what else does it give us? At a temperature of 315 Kelvin. R is always given to us, it's a constant, so that's 8.31. And then what we're solving for here is how many kilograms. Well, the only thing that we can really solve for here is moles, but then we can use our moles to convert to kilograms, like we've been doing in previous units. So let's set up our equation first. Like we've always done in the past, we want to rearrange our equation to set it up so we're solving for what we're actually looking for. So here we're looking for moles. So what I want to do is rearrange our equation PV equals nRT so I get moles by itself. How am I going to do that? I'm going to divide by RT on both sides. So I'm going to get PV over RT is equal to N. Now I just plug in the numbers that they gave me for it. So pressure is 1.50 times 10 to the 3rd. My volume is 2.24 times 10 to the 6th over R, which is 8.31, times my temperature. Make sure your temperature is always in Kelvin. Some problems might give it to you in Celsius, but make sure you convert it to Kelvin. So that's 315. So I do all this math. And I get N is equal to 1.28 times 10 to the 10 to the 6 moles of CH4. Alright, so now I'm in moles of CH4, but the problem asked me for kilograms. So I have to convert moles to kilograms, which means to grams first. So I do that by using my molar mass. So my molar mass of CH4, I add together grams of carbon with grams of each hydrogen. That's going to give me 16.042 grams of CH4. Now I'm in grams, and if I want to convert it to kilograms, I'm going to have to divide by 1,000. So that's 10 to the third grams per 1 kilogram. So I do out all this math. And I get 2.05 times 10 to the 4th kilograms of methane. Why don't you try the first problem on worksheet number 4 in your packet?